All right, we're looking at a problem involving acid and bases reacting. And we'll need to just kind of discern what type of problem it is. Is it one of those easy ones where it's just an acid and water? Or is it a strong acid, strong base combined? Let's read it and see. So we have 10.2 mils of a 0.125 molar magnesium hydroxide solution. It's first described. And right away, we want to note that we have with magnesium, it's a group 2 metal alkaline earth. We can say, well, it has a 2+ charge. And so really it's delivering, a strong base. We want to tag that as a strong base. So it's in the possibility of being a strong base with a strong acid, but let's keep reading. It's used to titrate to endpoint. Now that's important because then we know we have to have an equal amount of the acidic protons with the basic protons. So we're going to underline that. That's important in our ice table that we're going to generate. It's added to or titrated a 5 mil acetic acid. Now you don't know the name of this, but it's kind of give us an idea that we have an acid here because it's reporting a Ka of this acid. So whether you know the name or not, you can just know that you have some acid here, and it's most likely that this one bonded to an oxygen is the acidic proton. So we have just a monoprotic acid. It's not got two different, and most of your organic acids just have one acidic proton. So what we have then is a weak acid plus a strong base. So we know this is that one where you kind of have two ice tables or two things you have to worry about. You got to deal with that boom. We talked about taking that into account and dealing with that first, this strong base. We got to deal with it. And it's going to have some reactivity. We called it dealing with the boom. And then after you're done with that, when everything settles, you'll have to see what's left as far as how much of your conjugate base of this acid, or if this had been flipped and we had a strong acid reacting with a base, we have weak acid left. But once we're done, we're going to have just I'll just use our general representation for the conjugate base left. This A- will be left. And we're going to have to look at how does that react with water to come to equilibrium. So two reactions, kind of two ice tables, and then go to the law of mass action. So we got a lot. So let's split this in half and talk first about our strong base. And what we're going to do is, like we said, just get rid of the spectator ion. So we're going to calculate how much hydroxide do I have just from the information here. We're adding this to the acetic acid. I think we've done it maybe different in class, but it just might be the easiest way for students to get right to the point. What is it I'm really worried about? You're worried about this boom, the hydroxide. It's a strong base. So we're going to focus in on that. I think that'll help. And then we're going to have, of course, the conjugate base made as this takes off a proton and makes water. And this is, again, a reaction not of water, but the reaction happening in water, this first one. So we would set up our ice table, and we'll do that. And we're going to use moles, and just always kind of do that. It helps us when we get to chapter 13 on buffers. So we know we can take the mill amount of the strong base, and it's our, like say, our titrant. We can standardize a base solution. We've done that in lab, or will do it. So we can take our 0.01, because we moved the decimal place over 3 spots, 0.02, and times that by the 0.125. Molarity times volume in liters gives our mole amount. So we're going to have 0.00128. I'll say just for space here, it's 0.001275, but we'll just, for the sake of the calculation, round up. Now we know this. I think I've already made a mistake. We had to double the amount that we come up with, because this is a solution of just this one ionic compound. But within that compound, there's 2 hydroxides. So all I'm going to do is just times this by 2 And that fixes the mistake. We're going to say, oh, what we have, I'll just put a little post-it note over it. We have, instead of that 0.00128, we have 0.00255. So we're going to take and just do a little quick change. 0.00255. That's I did not mean to do that, but that's good. It just happens. You kind of catch yourself. Oh yeah, I had the hydroxide. There's 2 of them for every one of these. So I just had to double after I do this multiplication. I had to double the value. So we said that just gets it out of the way early. And now we can say, hey, I know this. I have to have the exact same amount of the acetic acid, because I'm dealing with the acidic proton here, and we have to go to complete endpoint or neutralization or equivalency. I have to have, for every one of these, I have to have one of these. And so we can just make it easier in the ice table. And we know the change is exactly that same amount. We take and go to equivalency. We had 0 amount of the conjugate base because there wasn't in the solution, and we don't care about the water, and we'd say plus 0.00255. And in the end, what I'm going to focus in on is this right here, because that's all I got left in solution is this 0.00255 moles of acetate anion that we kind of represented as our A minus. So what do we do now? Well, okay, we have to say, well, that does not just sit in solution happy. It comes to some equilibrium because we can see we have a Ka value for acetic acid, and if there's a Ka for acetic acid, there's going to be a Kb for the acetate anion. So what we can do, since we're given the Ka, we can use an equation that will probably be given to you. We'll use it enough times, you'll probably just know it. Where if we're given a Ka, but we really need the Kb, and you say, well, why do we need the Kb? Because all I've got left is that acetate anion in water. This is completely neutralized. So I can make a little bit go back. I can go back to this acetic acid. It's going to find equilibrium plus hydroxide. So I'm having a anion react with water to take a proton. Well, that's not a Ka issue, that's a Kb. So we can take and use not Ka times Kb is equal to 14, but 10 to the minus 14th. So what I'm going to do is use my calculator here, and I'm going to divide 10 to the minus 14th by 1.8 times 10 to the minus 5th. I'm going to angle it up so I can see it here. You might lose the screen, but I'll put it back down. I'm using, if you're watching, to raise that to the power, I can have this just 10 and then use this arrow and use some function to get to just quickly 1 times 10 to the minus 14th. So 1 times 10 to the minus 14th. So now I'm going to divide that by, and you have to be careful when you're using these terms here, scientific notation, you're going to have to use the brackets, I guess. So we're going to say 1.8. And then I'm going to hit this 10 to the x, and I'm going to say minus 5, and I'm going to double bracket that thing, and I'm going to get my final Kb value for this reaction. I'll worry about it later, but it's just going to put it down here. Kb for this reaction is going to be 5.56, we'll say, times 10 to the negative 10th. That's really small, so we're not going to worry too much about it coming back, going to this side, going towards the acetate, but it has some amount that's not 0. Okay, so, okay, fine, Dr. P. What do we do with this? Well, we take that 0.00255 as our initial starting point for the acetate anion. And I don't worry about water, and of course, I just finished the titration, and let's say we could stop it from coming to equilibrium and then turn it back on, and it's going to shuffle a little bit to the other side according to our Kb value here to make the conjugate acid from this base. And we're going to get some amount. Now, this is really not truly 0, but we're saying from this reaction and something over 10 to the minus 7th. So, because there's always auto ionization in water, yada, yada. But let's go ahead and say then, we know this is really small, Kb of the base in water, that's measured by Kb. That's how much does this reaction go? Well, 10 to the minus 10. So we can say X is really small, minus X. We don't care for water, but we do care for these two. So we can now say at equilibrium, it's roughly going to still be 0.00255 moles, and we'll have X moles and X moles with this. Now we're ready to go to our law of mass action. But remember, we need to always go to molarity. So to do that, we're going to have to come back to our amounts here in volume. And I skipped the initial molarity, and we'll come back to that. We're just getting the final pH right now. So 10.2 plus the 5 gives me 15.2 mils. But I know that I have to divide that. I have to move the decimal place. So it's going to be really 0.0152. So we're going to take the amounts of our product from this Kb reaction, products over reagents. That's X squared. And we're going to divide that by 0.00255 divided by 0.0152, because that's the liter amount we have of our solution that's left after this titration to endpoint. So now we're going to solve for X. Now I think at this point, for the sake of the length of the video, I'll put in the comments on this video what the answer is for both the X, that's the concentration of hydroxide. That's going to be X is the concentration of hydroxide. But I think at this point, most students can sort of round third and get on home with this. They just know that they have to take the negative log of this. So if I take the negative log of that hydroxide concentration, I can then plug it into the POH plus pH is equal to 14. I can plug that in, because negative log is P. I can plug that in, find pH, and find my answer. So I think for the sake of time and space, I'll just leave that. This is usually the hardest part, is just getting down to this point with the right numbers. And we've done that. But now you can solve for X. X is your hydroxide concentration. Take the negative log of X, and that gives you your POH, and then just subtract that from 14, and you'll have your pH. And this, because I don't want to let this go, the concentration initially of our acetic acid, they give us the volume, and we know what the mole amount was of the acetic acid. It was 0.00255. So all you have to do for this one, I'm going to put it in blue, and I'll put it right in the corner, because I don't think it really takes that much space. We can just say 0.00255 is the mole amount. We're going to divide that by we want the initial, so we're not going to take the total volume like we did here. It's just divided by the 5, but we change it still to liters. That would be moles per liter. We just have 0.00255 divided by 0.005, and that would give us our initial molarity of the acetic acid. Hardest problem that you'll have, I think, in chapter 12, where you titrate to endpoint or to equivalency. In this case, we did a weak acid using a strong base, but you can do the flip. You can have the strong acid and a weak base. This was the hardest one, though, because you're dealing then with what's left over. You're dealing with a Kb. So we had to use this Ka times Kb is equal to 10 to the minus 14th. And we did. We got our Kb here. And I hope you can solve for X. I'll put it in the comments what the answer is. Thanks. Bye-bye.